Hi there, guys. In this video, we're going to be looking at some use cases around the financial industry. So, for those of you who work in the finance sector or aware of things that occur within the finance sector, you will be very familiar with the fact that some banks and financial institutions get fined. And these are like several millions of pounds or dollars fines. And these fines usually occur because the banks are handling transactions they shouldn't be handling. And also, sometimes the banks are giving financial advice in scenarios where they're not authorized to give financial advice. So these are banks or financial institutions. And these fines can range from several hundreds of thousands of dollars to several million. I did a quick search on ChatGPT. So, what banks have been fined for providing financial advice? So, it just went through some articles, did a quick search on the internet. And long story short, we've seen Wells Fargo, they've been fined $100 million by the CFPB, essentially for opening accounts and just hiring funds without customer consent. Obviously, you can go and look into this article or this particular story. But we also have Rabobank, 12 million euros, and we have Singapore that fined several financial institutions for money laundering regulations and misconduct by relationship managers. So this is a real thing that happens and it costs financial institutions several hundred of millions of dollars and pounds a month. What we're going to do today is we're going to build a RAG pipeline that can ingest some information about some assets. In this case, this will be stocks of tech companies essentially. We're going to ingest market reports, and then we're going to create a RAG pipeline that can provide an output. And sometimes this output might include financial advice. And we're then going to use another model to then detect if the output of the RAG pipeline is providing financial advice or not. So when we do detect like a financial advice, another process could probably be taken to escalate the situation or the context. A lot of words, but let's put everything into context here. So I'm going to minimize myself. Too big. Yeah, that's better. Okay. So the problem statement, right? Financial institutions often face difficulties in reviewing any provided statements or advice for regulatory compliance. So, one, it can be very hard for you as a financial institution to manage the output of every single person within that institution to make sure they're not violating any sanctions or violating any regulatory or compliance rules. So what we're going to do is we're going to implement a RAG pipeline. The models we're going to be using today are Gemma, and we're going to be using another variant of Gemma called ShieldGemma. So we're going to implement a RAG pipeline, and we're going to implement a policy detector using ShieldGemma. And all of this is going to be explained. So the system will flag any potential violation. So there'll be an output from this pipeline that will basically output an indicator of if there's been a violation of a certain policy. In this case, do not give financial advice. The use case, for those of you who work based on use cases, is a regulatory compliance automation for financial statements. Or when I say statements, I mean like worded statements or advice or written statements in general. The value of this is this use case significantly reduces the manual effort needed to ensure compliance, and also it lowers the risk of fines and increases accuracy and speed of regulatory reviews. So we're essentially using an LLM to detect any violation of a certain policy for each output that LLM or a system provides. So this is what the very high level system architecture looks like. Let's start from this, but just to show you what we're going to be building in this video. So this is what we're going to build in the video. We're going to have a user input. And the user inputs is going to ask for some recommendation, some financial investment recommendation. And we're going to use the RAG pipeline to pull in some data from our knowledge base. And this is going to be the output of the RAG pipeline. Essentially, we're going to be using Gemma 2B to produce this output. It's going to be a text completion. It's going to be the text generation aspect of the pipeline. There's a bit of evaluation going on here, but I want to show you the content moderation, or at least we're moderating the output of the previous Gemma model. We're using the ShieldGemma 2B, and then I will be explaining what ShieldGemma is later. So ShieldGemma 2B And what we're going to do is specify a policy, and ShieldGemma will be able to give us an output if there's a violation of this policy with a certain confidence. So from the output generated, the content violated the policy that we set with a confidence of 62%. So in this case, the output of the Gemma model contains some form of financial advice, and the ShieldGemma model was 62% confidence that this is the case. So we can go into the code and we could go into some of the diagram and understand what we're actually going to be building here. I'm going to be going through the steps of this code. So there's 10 steps, giving you the full information of how this is built and how we got here. And all the models we're using are open models. You can access them from Hugging Face and you can host them locally. So we go in here. So I think we're done with cancel that. Let's go into this diagram very quickly. So in a typical RAG pipeline, you have your data source. In this case, we're going to have our data source from Hugging Face, and we're going to clean and prepare our data. And mostly we're going to take our data source and divide the source of text into chunks. And these chunks would then be passed into an embedding model, which would generate a numerical representation of whatever chunk, which will be text that and passed into. Then alongside the metadata of the chunk with the output of the embedding model, which would be a vector embedding, we'll combine this into one object and then ingest it into MongoDB. So we're going to do this process we're going to create a metadata plus embedding pair for every single aspect of chunk from our data source. So this is just a simple ingestion pipeline, and we're going to ingest it into MongoDB. MongoDB here is going to be our operational and vector database. So we're going to have MongoDB handling all the vector embeddings alongside our normal transactional data that you will have in a normal application. And the reason why you would use MongoDB in this case is you're able to perform vector search queries alongside your typical traditional queries you can do with such as text search or lexical search. So that is the ingestion process of this pipeline. Next, let's go into the aspect of retrieving, or maybe the aspect of a user's perspective. So a user here, zoom in, will enter a prompt, and this prompt could be a statement made to like a financial advisor or financial system like a chatbot. And we don't want to make sure that chatbot is not giving out any financial advice, or we will get fined by the powers that be. So a user prompt could be, hey, what stocks should I invest in tomorrow to double my money? Essentially, you don't want to build a chatbot that spews out financial advice when given this prompt. So the user prompt will be embedded using the same embedding model over in the ingestion process. In this case, we're using GTE large, more on that later. And then when we generate this embedding from the user prompt, we're going to perform a vector search query to retrieve the top K documents that are semantically similar to the documents within our MongoDB collection from the data that was ingested in the ingestion pipeline. So this is just the retrieval step. So once the documents have been retrieved, you can see the arrows pointers are kind of small. I need this a bit bigger. But once the documents are retrieved, they're supplemented with the user prompt, right? We supplement that with the user prompt, and we're going to pass that into Gemma 2. So Gemma is a lightweight open weight model that have been released and trained by folks over at Google DeepMind. And there are models. Gemma is a family of models that were trained using the same architecture as the Gemini model, which is Google's more powerful, robust large language model, well, multimodal model at this point. So we're going to pass in the user prompt and the retrieved documents into Gemma, and Gemma is going to give us a generated response. And so there's some things you could do here, right? In the pipeline that I've created, we send the response directly to the user, but also we then run another sequence or another operation where we pass the response to ShieldGemma, which is a variant of Gemma 2, and we get like a policy violation score, policy violation output. One thing I could have done is we could have just said, okay, we're not going to do this, right? We're not going to send a generated output. we're just going to send this generated output to Gemma or to ShieldGemma. And then in the policy violation score, we can set like a threshold, right? So if the threshold is less than, let's say, 70%, right? So if it's the threshold of it violating the policy is less than 17%, then we can actually send over so we send the generator response to the user, right? And if not, then we can then do, I'm sure there should be like a decision or diagram here. So if not, we can then do we can have an arrow here, just say flag for, right? Okay, so greater than, if it's not violating a threshold, we send a generator response. If it is violating the threshold, or there's a high confidence that it might be, we send it over for a review process, and we maybe generate like a canned response to the user saying we can't respond to this certain query, or we can't support this query at this moment. So anyway, that is essentially that's the architectural high level overview of what we're building. But now we're going to go through it in code, and I'll show you all the different components here. At this point of the video, right? If you're someone that just likes to read, you can actually get an article version of the steps I'm going to be presenting to you over in this MongoDB Developer Center article. So I've written this 20 minutes to read. It's extensive. We've got some good diagrams. I explain what Gemma is, which is a family of lightweight models, and they're built with the same architecture and building blocks as Gemini. We talk about some use cases, and I talk about what's covered in this article, mainly the key components of a RAG pipeline. So that you can see here. So this article will be in the description and in the comment section at the top. So let's talk about the code. Let's go to the code now, right? We might as well just jump straight into it. There's 10 steps, 11 steps. I'm going to be showing you some evaluation using DP vals. This is essentially using LLM as a judge. And well, to be honest, we're using LLM for both the evaluation and moderation of the content. So this is a good example to show how you can use LLM in different scenarios or different processes within a pipeline. So let's start at the top over here. Oh, another thing you probably want to know is this code is going to be available in the comment section, but you can get this code that we're presenting right here and more over in the Gen AI showcase repository. And you can do me a favor, giving you this resource for free. If you could just leave a star, fork it, and just use the content in this repository. We cover thumbs up. We cover a lot of different stack components, stack combination, and we have a collab and some articles or some use cases have articles and code alongside. And we cover agents as well. So agents are becoming a thing. AI agents is being covered in this repository as well, and many more aspects, including data sets. So yeah, so this repository is the best repository for a AI developer. And let's go back into the code. I'm gonna close this. I'm gonna start from the top. So I'm gonna take you step by step and explain in detail what I'm doing here. But for those of you who feel like you've got the gist of this and you want to see maybe Gemma in action, you can get the Google Collab and run the Google Collab on your own. But I appreciate you following me along in this video. So let's go. So the first step is we're going to install a bunch of libraries and we're going to set some environment variables. So we're going to install the datasets library. This is going to allow us to access the dataset on Hugging Face. We're going to have pandas. This essentially is a Python library that allows for some not complicated, but very computationally efficient modification of Python objects. So, and it also allows for data visualization as well. Very simple data visualization. And PyMongo we're gonna be using the methods and classes from this library to access our MongoDB database and collection. And then sentence transformer is a library from Hugging Face, from the folks over at Hugging Face. We're going to be using that to access the models, the embedded models and the models we're using within this process. And DP Vials is going to be the evaluation framework we're going to be using within this pipeline as well. And all of this will be explained in more detail later. So the first thing is to just set some environment variables. So you're going to need a Hugging Face token to access some data from Hugging Face. And you can go to this link to get some information on how to retrieve your Hugging Face token. Then you're going to also need an OpenAI key. Yes, I said we're using open models, but for DP Vals, you could use OpenAI as you can use GPT as the LLM as a judge within the evaluation framework when you're using DP Vals. But you can also switch the model selection within DP Vals within the config. I've never done this before, but you can just switch it out easily as well. If you don't want to do an evaluation step, then feel free to not even execute this block of code. So that is all the environment variables you have to set up. Next, we're going to go into the data loading and preparation process. So in order for us to mimic a scenario you might find in financial institution, we're going to use a data set that contains different companies and their market reports. Because based on market reports, what financial analysts or asset analysts would do is read a market report and then decide if this company is worth investing in, or use the market report as a factor that contributes to the decision of if a company is worth investing in. So we're going to we're going to load data from Hugging Face where we have some market analysis reports of a certain company. And these reports are extensive. And they will also have some more information, such as the stock price and price to earning ratio and whatnot. So these are just information of a company. So this is what it looks like. You can access the data set over here. It's a very small data set. And what we have there is very simple. We're loading the data set using Hugging Face. We're going to actually stream it so we can use the take method to specify a specific amount of data we want to load in. So here we're just going to load in 100. I think there's only 63 data points. So I don't know why I'm doing that. We're going to load the data set into a data frame, a pandas data frame. This then allows us to do some visualization and some very simple efficient operation on the content within this data set. So let's see, we're going to see what the top 5 data point looks like. So here we have the recent news, which is just a very simple headline. And we're going to have the reports. So the reports are basically author, and we have the reports content as well, which is like an extensive corpus of text. We have the name of the company and the ticker symbol, and also some key metrics of the company, which includes the stock price, the high and low of the stock price on a 52-week range, and the sector of the company. One thing I do want to let you guys know is this is all fake data. This is synthetic data generated by an LLM that I created, essentially. This is not real. This is fake news. These are fake companies. But next thing, now that we have our data within our environment, so this data is going to be acting as our knowledge source that the Gemma model can pull from to answer users' query. So what we're going to do is go through like this data preparation step I was talking about. Very simple preparation step. And what I mean by preparation is we're going to prepare a set of content that we're going to embed, but we're going to use for our embedding process. So the selection of the attributes that I want to use for the generation of an embedding, a vector embedding, the attributes have to be able to contain or at least encapsulate a meaning of the data point. So I'm going to combine, here I'm combining the company and the sector role, and then I'm combining all the information from the reports as well, because there's a lot of context, there's a lot of semantics about the company, and the general, I guess, information or the general information about the company is all within this report. So I'm going to get the information from the report of both years for any years in the report. I think we have 2003 and 2024. I'm going to combine it into one string and then combine other aspects of the recent news as well, because that's important as well. That's more context. I'm going to use all of this to generate the embedding. So I'm going to create a new attribute within a data set called combined attributes. Very imaginative. And I put all of this into a function called combined attributes. Again, function name, very imaginative. So what's going to happen is for every single data point that we have within our data set, we're going to combine the relevant rows and create a new attribute, a new attribute for every single data point called combined attributes. So here we're just going to view the combined attributes after we've done this process. So we're going to view the ticker, and the combined attributes. Here we have the cyber defense dynamic, which is the company, and this is the attributes that contains all the information we've concatenated together. And this is what we're going to use to generate our embedding. One thing to note is, what did I not use? So I did not use this information, which is the key metrics like the company stock price, the high and low. I think this will get lost in the high dimensional space of the vector embeddings, really. But what we can do is, because we're using an operational database and a vector database in one, which is MongoDB, we can always do some traditional search on this field, which is sufficient as well for retrieving some information. But that's a different story for another day. Let's focus on generating the embedding. Step 3. What we're going to be using is GTE Large. So GTE Large it's an embedding model created by the folks over, research scientists over at Alibaba. I think it's based off the BERT model. Don't quote me on that. But very quickly, I'm using the GTE Large. Let's look at it over here, actually. Yes, this is the GTE Large. Let's zoom in. Excellent. So this is the GTE Large embedding model. And what we can see here is right here. So too much? Okay. Right there, we can see the model size, less than a gigabyte, half of a gigabyte, or just about half. But the output dimension of the vector embeddings are 124. Secret lenses are 512. And you get the scoring of the embedding model on different tasks, such as clustering, classification, re-ranking. Retrieval is what is relevant to this current video, this current tutorial. We're very interested in the retrieval score of this embedding model. But one thing you can also do is, on Hugging Face, you have this leaderboard where you can see a bunch of models plotted against each other or ranked against each other, and you can see essentially where the embedding model you want to use and that you want to use, where it ranks. So we also have, again, put this down. So we also have some similar task for the evaluation, classification, clustering, re-ranking, retrieval. And if this is right, we can see where GTE Large is. So GTE Large. Okay, so GTE Large is, well, it tells us the parameter size, which is called 1024 is a dimension, and we know that already. We know the retrieval is around 52.22. I thought it would show me where it's ranked. Oh, it did. It does. It's ranked 51. So GTE Large is ranked 51. Let me see which version I'm using. I'm using the version 1.5. So let's go the English one. So this specific model has been trained for English text only. So this specific one ranks 26, which is decent, quite high up. I'm choosing GT Large because it's one of the best performing open models out there, open source models out there. And that's the only reason. You can try anyone and see, evaluate its performance. So we will go back to the code. So we're going to load the GT Large using sentence transformer. We're going to import the sentence transformer module and load the GT Large English version into our environment. You have to specify this as true, or you won't download into your development environment. Long story short, what we're doing in this process is we're getting the text, which is here. We're getting the input data, which is the combined attributes. Remember the combined attributes? We're going to pass it into this function, and this function is going to pass it into, essentially, it's going to pass the text into GTE Large, and the output of this is going to be an embedding, a vector embedding, which is basically a numerical representation of the data input or the input data. So in a separate video, I'm going to talk about chunking and different chunking strategies. But for those, this is commented, so you can look up what chunking strategy I'm using here. So one thing after this whole process is done, the generating of embedding, it's relatively quick, very, very quick, doesn't take too long. Only 63 data points here. What you're going to get is a new attribute, a new column, and which will have the numerical representation of the combined attributes. So this has been passed into an embedding model, and we're able to generate this. Now, this will allow us to conduct a vector search, right? So with this information, we're gonna have a high dimensional space where two vectors that are semantically similar or similar to each other are close in distance. And using some mathematical equations or functions, we can calculate the distance and then give a relevant score or similarity score as the output of the vector search operation. So we're going to talk about that later on. But let's talk about MongoDB, the vector database, and how we can connect to MongoDB. So first things first, you can register to MongoDB for free, and you can create your MongoDB Atlas account right here, clicking on this link on the notebook. And if you follow the instructions on this link, you'll be able to deploy your first cluster. And then next thing what I want you to do is create a database called asset management use case. And within the database, you can create the collection market report. And I'm going over this, but I'm going to show it to you in a second. So, and also when you're within your MongoDB Atlas account, you need to also get your connection string, and the steps to get it is right here. So let's go over to MongoDB. I'm going to need to. All right. So we're in my MongoDB account, and we can see I already have the data. Ignore that. I'll show you this later in a second. So when you go into your MongoDB account, if you're logging in for the first time, you might be visited with a page like this. If you have an existing cluster, maybe you're just an existing MongoDB user and you're trying to understand how you can build RAG pipelines, you can get your connection string very easily. Very good buttons that can help you create your database and create your connection string. So first things first, let's see how we create a database. So if you click on the database here, you can see a create button over here. Click on the create button, and what you do is you create your cluster, and your cluster can actually see anywhere else. So I'm not going to get a free cluster because I think I've used up all my free cluster, but if you're registering for MongoDB for the first time, or maybe you're an existing user, go into the shared and you can get free clusters in the shared tier. So one thing with MongoDB, you can have your MongoDB database or your MongoDB cluster sitting on any of the top 3 cloud providers. So we have AWS, Google Cloud, and Azure. So you can place them anywhere, with any cloud provider that you're working with, maybe your organization works with already. And also you can place them in any of the specified regions, essentially. It's important as well. But once you're done, that should be enough for the free tier version. But some of you might be in the more advanced. I want to maybe increase the power or at least the compute of your cluster, so you can go for a more powerful cluster. And then there are more additional settings such as turning on backups, your data is backed up. So when you're on the free cluster, you should be able to create. When you're on a free account or you've created a free account, you should be able to create your free cluster directly. Okay, so let's cancel this because I'm not going to create one. So once your cluster has been created, it might take a few seconds to get your cluster to get created. You can then browse collection. So this essentially will be empty for you. So you want to create a new database within your cluster, within your server, essentially. You can just create. Let's go back. You can create data. You can click on the create database button and then just write in the database name, which in this case is the asset management use case, and the collection name, which in this case is market report. And ignore this, and this should be enough, right? And you click create, and that's it. And that's all you needed to do for that step over there. Leave a comment in the comment section. Get stuck. So, okay, let's go back to the code. So once you're done with creating your database and creating your collection, what you're going to do is get your connection string. And let's go back to MongoDB. So to get your connection string, and some of you might have seen this already, if you click on database, within your cluster, you can click connect and go to drivers. And we're using the Python driver here. And you can see this is what your connection string is going to look like. You're going to need to replace the DB username and DB password with your username and password. Where do I get this information from? Well, over here in database access, you click into it, you're going to see the users that you've created and the password allocated to those users. So that's it. Another key point to note is in your network access, if you're working from a Google Colab, you probably want to allow IP address from anywhere for a limited time while you're testing out your notebook. So this instruction is also specified in the article as well. So once you get your connection string, you would just put that into this Google Colab. And if you get stuck at locating your connection string, do reach out to me on the comment section or on LinkedIn or something. So we're going to be using PyMongo to get an object of our cluster, which will allow us to access our database and collection. That's what this step is just doing. Very simple. So what we're doing here is we're creating a client, which represents our cluster. We're going to ping it just to make sure we have a connection. Then we're going to retrieve the Mongo URI, and the Mongo URI will be passed into the function get Mongo client, which will get us the client. And next thing we're going to do is specify the database name and specify the collection name. Excellent, all done. So we're then going to say Mongo client.get database, which would be the database name, and db database.get collection and the collection name. And that's so we have a database object and we have a collection object. So with our collection object, one thing we could do is just delete any existing records in the collection. So we can use this batch method operation called delete many, and this would delete all the any data within your collection if you're maybe rerunning this again. As you can see, when I ran this, there was 0 data deleted because I was running it for the first time. And that is the connection to MongoDB done and simple. So the next step is to actually ingest data into our MongoDB database. So we're going to be ingesting the metadata that we have from our dataset, and we're going to be ingesting the embedding that we have from the embedding generation step. And every metadata for every chunk will have a corresponding embedding, and they're all going to live in the same document, which is kind of cool. So this is just going to explain why MongoDB for your AI application. We're talking about the document-oriented structure. We have JSON-like objects, and that's how we represent data. So it's very familiar, especially if you're from web development or if you work with APIs. The way data is stored in MongoDB will be very familiar. Also, we have this efficient ingestion, and I'm just going to show you the lines it takes to ingest data into MongoDB. 2 lines, apparently. So 2 lines, we assign a variable called documents to a dictionary object of our data set, and then we insert this into MongoDB, right? We call the insert many from our collection, and we set the documents into our collection. And that's it. 2 lines, no transformation, serialization, or anything. So what does the data look like in MongoDB? So here is what it looks like. Let's go browse collection, zoom in. Okay, so this is what the data looks like, right? A single data point contains the recent news report, and this was the report I was talking about. This will be 2023, and this one here will be 2024. And then we have the company name, the ticker symbol. But let's see what a report looks like. A report is going to have the author, it's going to have an extensive content, a title as well. All of this was concatenated to essentially create a text that we can create this embedding on. And here is the embedding, numerical representation of our combined attributes over here. So you can see you have this embedding data and your normal transactional data just living in the same database, in the same collection. No need for like a specialized database on top of your operational database, or even installing extensions. So this, you can actually conduct a different type of query with this data, including vector search and text search. So that's what the data looks like in MongoDB. And we have 20 of this, and actually we have 63 of this because we have 63 data points from our data sets from plugin phase. So going back to the code, we've ingested data, right? So far, let's recap what we've done. 5 steps. We've loaded libraries into our environment. We've loaded our data. We've prepared our data. We've generated some embeddings. And then we've also connected to our MongoDB database and ingested the data into the MongoDB database. The next thing we have to do to make everything all come together is to create a vector index. Essentially, an index is a data structure that allows for the efficient location of some of the data you have in storage. So this is what an index is. So what we're going to do here is we're going to create a vector index that will allow us to essentially conduct a vector search. So here I'm creating a function called setup vector search index. Again, I'm very good with names. So we're just going to use, again, a PyMongo function here called a PyMongo class called search index model. And this will allow us to create, essentially allows us to create an instance of an index. And the index is going to take in the index definition, the index name, and the type vector search. So you can have a bunch of indexes in MongoDB. You can have a text index. And here we're just going to have a vector search index. So what we're going to do is we're going to, from our collection object, remember our friend collection here, we're going to call the create search index method and pass it in our index model over here. And this will create the vector index within the collection. And now we can do the magic of vector search. So that's the function. So what we're going to do is actually create the index definition that we're going to pass into the function up here, because we need a collection, we need an index definition, and we need an index name, and the default will be vector index. Okay, so what does the index definition look like? It looks like JSON. It contains the field or fields, which will be the fields that you're creating the index on, the type of data within the field, which will be vector, the path of the field, which is the attribute name of the field, which is embedding, the number of dimension. This is the number of the dimension size of the embedding within the document. Here it's 1024, and this is the dimension size from the GTE large embedding model. So next will be the similarity function we're going to use to calculate the distance between two vector embeddings. Here we're using cosine. So we're going to then call that function setup vector search, and we're going to pass it the collection that we have. And we're also going to give it the vector search definition, index definition that we just defined up here. And the name as well is going to be vector index. Don't know why I specified the name. Anyway, the name is going to be vector index. So that's it. Now we can actually start creating that vector search functionality. What we can see here is I've put some information to explain the MongoDB query language, how familiar it is, and some of the usual stages or operators that you will encounter as a MongoDB database user. So this is extensive, but you can also get more information on the MongoDB docs. I want to talk about the vector search function. So next step we're going to do is we're going to create a function that allows us to say, based on the user input that we've created an embedding on, we're going to use that input as a query vector and conduct vector search against all the vectors, all the vector embeddings within our collection in MongoDB. And then we're going to retrieve the ones that are similar to the query vector. It's that simple. That's what this function here is doing. So we're taking the user query and we're taking the collection that we're going to do the search against. So here we have the user query and we're going to embed it. We're going to get the query embedding or the query vector, whatever you want to call it. We're going to use that get embedding function we used earlier on for our data set. We're going to use it for the query as well. It's very important to use the same embedding model for both when you're querying and when you're ingesting, and also when you're actually conducting your query. Make sure you're using the same embedding model with the same dimension factors. So next, we're going to use the vector search operator. And this is a stage. So what happens is the way you can think of MongoDB and how it operates on data is we have processes that can operate on data, and these processes are called stages. And the first stage we're going to have is the vector search stage. And the vector search stage is going to use the vector index we specified earlier on, make sure the name is exactly what you specified earlier on. And we're going to use a query embedding we just generated and specify the path in the collection that we want to conduct the vector search against, and specify the number of vectors that we want to consider for this similarity and similarity search. And we're going to specify the number that we want to return. I'm only going to return 2. Don't need to be extensive, but you could change this number to as return as many as you want. But obviously, this number here cannot be greater than this number here. So that's what we're doing with this vector search operation, and that's it. So we create a vector search stage, and then I'm also creating an onset stage. This is not necessary, but I just wanted to show how you can exclude a specific field. One, the embedding is very large, and I'm not going to be using it in downstream processes within this notebook. So I'm just going to remove it, which can obviously alleviate some of the database operation. Here, I'm showing you how we can include certain fields. So the onset stage we can exclude, but with the project stage we can also include and exclude. But you can also, the only attribute you can exclude while you include is the ID. So we're going to include the company reports and combined attributes. Really, if I have the combined attributes, I don't need the reports because the combined attributes contains the reports and the company, wherever, data overload. But one thing here is, which is important, we're going to include the vector search score, and this is going to represent the similarity of this document that was retrieved against the user prompt that was fed as the query embedding. So here, we can actually create a list and then pass in our stages that we've just defined in the order we want them to occur. So your vector search stage has to go first. Then you have the onset stage, which removes the embedding from the return documents. Then we have the project stage, which includes the attributes you want to see as output. Now we can execute the search by calling the aggregate function or method on our collection object and passing it the pipeline. Right? I've called it a pipeline. It's how you think about it. But this aggregate will execute each of the stages, and the output will be a list of documents from our collection that are semantically similar to the query vector or the query embedding or the user prompt, whichever level you want to see it at. So I just have some boilerplate code here called get search result, where we actually pass in the query and then we're passing the collection. So what we're doing here with the get search result is the query here will be the user statement. So this could be the statement that comes out from a user of the system, and the user could be a customer using the chatbot interface, or you can also have the user as an internal employee of a financial institution writing into a document or into email or something into the system. So that's who the user is, and then we pass this in as a query, and we specify the collection we want to conduct the vector search against. Here we're using the vector search operation we specified in the previous cell block. Then from the get knowledge, again, naming, not that great. So from get knowledge, the variable get knowledge, this is going to contain the documents that matches, semantically anyway, this query. What do you need to? So we're going to then do some formatting here where we get the result and we structure it in a certain way. I'm only going to return the company and the combined attribute. And you can see I'm not really using that report that I said earlier. So I don't know, you can experiment with removing it. So here we can use all the functions we created. So we have the query, and the query is select a company from the provided information that is safe to invest in for the long term and provide a reason. So this customer or user is asked for financial information. I remember our use case, right? I've asked for financial advice. I remember our use case is to create a system that can detect when a financial advice has been given. Here, what we're doing is just, I'm giving you an overview of a RAG pipeline within a financial institution, just to show you how you can implement this very, very, very simple. It's very simple to implement with MongoDB. So here we have the query. Great. And then we assign the result of this get search result function over here. We're going to assign it to source information. That's what the variable is called. And then we're going to combine everything, the query and the information, into a variable called combine information. Now, this combine information is what is going to go into Gemma. We're going to pass this into the LLM, into, Gemma 2B. This is RAG, Retrieval Augmented Generation, supplementing the user query with information that has been retrieved from a knowledge source. That's the source information. And the method of retrieval in this case is vector search. So here we're going to print it just so we can see what it looks like. And here we can see we have the query, and we have the statement that says continue to answer the queries and the search result. And then we have the company, and this is going to be the information context for the LLM. So one thing we're going to do now is load Gemma 2. So we're going to be using the transformers library, and we're going to be loading Gemma 2 from Hugging Face. We're going to load the tokenizer, and we're actually going to load the model. So the tokenizer will take any of the text we have and transform it into tokens that are familiar by, or transform into tokens that are recognized by the Gemma 2 model. And the model is the actual Gemma 2 model itself. Over here, you can place in device map auto as an argument here if you have access to a GPU. And if you're using Google Colab, you can change the GPU, your compute settings over here to use a GPU. Or else this process can take a little bit long if you're using this computing configurations, or if you're using the A100 with high RAM. So next thing we're going to do is just, this is boilerplate code to extract the model response from, on that note, I can go into Hugging Face and show you the Gemma 2 Hugging Face page. So it's over here. I'm going to link it in the description below. Over here, you can see here we have Gemma 2 is a family of lightweight models created using Gemini models. We said that earlier. And this just shows you some example code of how to utilize it. Back to the code. So now we're going to specify like a chat variable that has a dictionary of the role and the user, and also the content, which is the combined information that we had previously. All of this is then going to get passed into Gemma 2. And what we're going to do is use our extract model function to extract the response from Gemma 2. The response from Gemma 2 will be tokenized as well. We'll decode the response because it's going to come in the numerical form, and then we need to revert it back to text. So we asked Gemma to provide us. So just to recap what the query was. Select a company from the provided information that is safe to invest in for the long term, and provide a reason. So out of the two companies that we returned, Gemma is going to select one, and it's going to give us a reason for us to invest. So here we're going to look over here. So we're saying base Gemma 2B, very small model. 2B, 2 billion parameters is a small model. So it's going to say, based on the information provided, it will recommend cyber defense dynamics. Okay, fake company. And it gives us the reason why. And this reason is obviously been extracted from the market report and the recent news and information that we've provided it as context. So it's also saying, wow, there are some challenges for this company, such as highly competitive nature or blah, blah, blah. I'm not a financial person. I'm sure this makes more sense to someone with a financial mindset. It also tells us it's important to do our own research and consider your personal investment goals and risk, which is good. It's telling us not to use his advice and do its own research. But one thing we want to know is, does this violate the policy that we're going to set? Because we want to detect if this is actually giving advice for financial investment, right, to the user. Because if we can't detect this and we give this to the user, we are going to get fined. So I'm going to skip this evaluation process, but I've explained what the metrics I'm using for the LLM evaluation. I'm only going to evaluate the generation component of the LLM. So we evaluate the answer, and we evaluate the answer in terms of relevance to the context provided, and we also evaluate how truthful the answer is or faithful the answer is to the context provided. So, so I'm just going to skip those. You can read it or read DP-Val documentation. But now we're going to use the other version or variant of Gemma, which is ShieldGemma. So ShieldGemma this is the page over here. Gonna link in the description for those of you that are interested. So ShieldGemma is a set of instruction tune model, but very specifically, we can use this model for evaluating the safety of a text prompt input and text output against a set of defined safety policy. Basically, guardrails, I think. Let's go. So basically guardrails, or at least we can set a policy and check if the policy has been violated based on the input that is provided. So I'm going to set the policy here, and this policy is going to basically, I'm creating a function called moderate content. It's going to take in the user input. Well, in this case, this is more of the model input. So this is a wrong name, but hey, it's some form of input. So we're going to use this input and we're going to specify the safety policy over here. Now, the policy is no financial advice. The content shall not contain or seek generation of definitive stock or asset recommendation to buy. This includes, but is not limited to, explicit instruction to purchase specific stocks, cryptocurrencies, or other financial asset. Very short policy. Obviously, in real life, these policies can be 10 PDF pages long. So here, I'm also specifying a prompt for the ShieldGemma, telling it that it's a policy expert and whatnot, and it's meant to detect any violations. So we're going to use some of the Gemma tags. So it detects when the start of the human turn is and when it can then starts its response. So long story short, we're placing the safety policy into the prompt that we pass into ShieldGemma. We're going to load the tokenizer and we're going to load the model as well, which we already did in the previous step here as well. So over here, you can see here I'm setting the threshold as needed. So I'm setting the threshold to 0.5. In this outputs a probability score that contains 2 digits. So I think the first one contains a probability of it violating, and the second one is probability of it not violating. So anyway, I set a threshold and I say, hey, if the score is greater than a certain threshold, then it violates the policy, right? If the first attribute is greater than a certain threshold, it violates the policy and we pass the score. If it's less, else it doesn't violate and we pass in the score. So this is the output. This is us using it. This is me using it. We're going to unpack the output of this moderate content function, which is going to give us the violate policy, which is a Boolean, true or false, and then the confidence of the violation probability. So if it violates the policy, which it does, it would then say the confidence at which it thinks that the policy has been violated by. So the output from the Gemma model, the ShieldGemma is basically 62% confident that this violated the policy we set over here of no financial advice. So the next thing you could do is maybe create an escalation process where if the confidence is above 62, this can then be escalated further down, or there could be an alert that basically alerts some account owners or whatever security or some of the folks in the financial institution to pay attention to with this conversation that's currently ongoing. So that's the in a nutshell, right? It's been a long video and a lot of it is mainly just explaining stuff. And we're using 2 models there. Well, 3 models if we count OpenAI GPT that we're using for evaluation. But here we're using Gemma model for both the text generation and then content moderation. And Gemma is an open way model. You can host it locally. And yeah, this was fun to create. Let's go back to the diagram. We can end over here on the diagram. Here we go. So this was fun to create. So we're using Hugging Face for the data source, Hugging Face to load our embedding model, and we use Gemma for the chat text completion and also for the content moderation here. So this was fun. This was fun. I think for the next video, we're gonna see how we can make this agentic, right? We make the whole process We'll make the whole process automated and let an LLM decide when to do a transaction check and access the its knowledge source. And we just make it agentic. Why? Because we can. Because we can do that. And I'm also going to talk about quantization as well. So this is one of my latest article that came out, and it was done with one of the talented engineers we have over here on MongoDB. And we're using Cohere's quantized vectors and ingesting them into MongoDB. And then we show how you can still get the same performance, or at least a semantic search ranking with quantized and non-quantized vectors. And I'll put it there because don't want to load you with too much information. One thing you could do is I can subscribe. I always forget to say that. Why? But like and subscribe if you found it informative, and have fun and happy hacking.